Okay, so welcome to the AI and Optimization Seminar. Today, it is my great pleasure to introduce Yuejie. So Yuejie is now a professor at Yale Statistics and Data Science. Yuejie is an expert in signal processing, and he is actively working on the theoretical and algorithm foundation of data science, scientific AI, and reinforcement learning. Okay, Yuejie, the floor is yours.
All right, thank you so much. Thank you for Li-Jun for the kind introduction. So I'll be talking about transformers today, particularly the training dynamics underneath the so-called chain of thought reasoning paradigm. This is based on two joint papers with my wonderful collaborators. So Tong and Zixin are my students at CMU. So I just joined Yale last year. So my students still, that's why you see CMU students. And Yu is a student at Penn working with Yuxin. Yingbin is my faculty colleague at OSU and RT at CMU. All right, so let me get into the meat of the talk. I don't think I really need to introduce large language models these days in the talk, but this is sort of next word prediction paradigm. But surprisingly, it has been making tons of breakthroughs, not just for the original language tasks it was designed for, but also for a lot of other scientific applications. And last year, there was a paper published in IEEE Spectrum where they did all sorts of benchmarking, and they made this verdict that they are seeing the performance, the capabilities of such models are doubling every 7 months. I would just leave it to you to determine whether this is an aggressive prediction or very conservative prediction. But I think we can all agree this is very impressive results that we're seeing in the last several years around transformers, language models. Underneath these large language models, transformers is sort of the backbone architecture that's driving a lot of the success. So for today's talk, which is more on the theoretical end for understanding sort of the mechanisms behind these architectures, I'll be taking a slightly simplified view of these models, so that I think it's sort of good for me to maybe think about how it operates. So the way I'm going to introduce these models is essentially this is the kind of sequence-to-sequence models. So if you still remember the toy example we have in the first slide, thinking of this sort of next word prediction, in your input, you have this chunk of words. So each of the words essentially giving you a high dimensional vector in a high dimensional space because you'll be embedding them in some vector space. So your input is some sort of a two-dimensional data matrix, where on the X dimension, you have all the different tokens, either spatially or temporally organized. And on the Y dimension, you have the high dimensional feature embeddings of these words. What transformer does is basically it takes this two-dimensional data matrix and map it to another data matrix of the same dimension. And along each of the dimension, you'll be applying different operations. So what the transformer look like is sort of a concatenation of what I call this transformer blocks. You can have many of them, so you can have a very deep architecture. But each of the block essentially is composed of two operations. One is a attention operation that essentially try to look into association on the token dimension, so the tempers, the x-axis of your data matrix, with the hope that you'll figure out, interesting correlation, the association, so you know which word will be important for you to predict the next word. And what the MLP does is it will be trying to manipulate things on the feature dimension, on the y-axis of your data matrix, so that you can think about how to best embed your data in higher dimensions so that it helps you to extract useful information. As you can take this transformer to be deeper and deeper, so hopefully you get sharper and sharper information that's being extracted both along the token dimension and along the feature dimension. Right? So that's sort of my high-level perspective of what this transformer does. And how does it do this kind of autoregressive decoding that you often see in practice? It's essentially at every time you have this input data matrix, and your transformer maps this to another data matrix, you simply take the last column of the output and claim that will be your next word prediction. And then you just append this back to your input. So input becomes one dimension longer on the token space, and then repeat this over and over. And by doing this, you get the so-called autoregressive decoding, so that language models can produce longer and longer answers. And this leads to the so-called kind of, thinking about chain of thought reasoning, where originally, this is really started as a mechanism trying to think about elicited reasoning patterns of these language models so it can start to answer harder questions. At the beginning, this is used as a prompting mechanism. So the way this works is if you ask the model some mathematical question, instead of asking the model to answer it directly, rather you ask the model to think step by step. Don't rush to get the answer out. So the model will actually try to answer a little bit longer, right? So you do a little bit more test time compute, and the answer structure looks like it will first give you some sort of rationale behind how to answer this question before it answers the question. And this all of a sudden dramatically improves performance of such models on reasoning tasks. And if we can do this by prompting, why don't we just try to train the model to reason longer? And this leads to this so-called test time scaling that people start to see that as you give the model more test time compute, the reasoning performance of these models has been shown to also increase proportionally. So this is just a illustrative example I scraped from one of the papers, the S1 paper, where they show that basically if you give the model more thinking time, the performance on various benchmarks on math or physics starts to increase over time. So this raises a question, why this kind of chain of thought reasoning can actually lead to better reasoning performance? There has been a lot of interesting answers to this question from the theoretical perspective. So particularly in the theoretical computer science community, people have been trying to think about answering this question from the representation power perspective. So asking the question, if you are given some kind of, say, constant depth transformer model, and you ask what kind of circuit or functions the model can represent, when you use COT, use a chain of thought reasoning, versus you don't give the model the capability to do this kind of COT. And it turns out that there is a very interesting divide in terms of capabilities of such models. So if you do not allow the model to do any of this kind of COT, then the strictly the type of functions circuits you can represent is strictly smaller than this what is so-called TC0. I don't think that the details matter that much here, but this is essentially a problem that you can kind of think about can be parallelized. Those problems such like parity, for example, checking parity given a string of binary inputs. On the other end, if you start to let the model to have increasing capabilities of chain of thought reasoning, so if you allow the COT length to grow, for example, linearly or polynomially with a dimension, then you can, strictly speaking, represent much more complicated classes of problem like NC1 and polynomials.
So what does it mean? Does it grow linearly with the dimension of what?
This is the dimension of the input. Yeah, I could be wrong there, but I think that's what it is. Yeah, so there is this widely believed conjecture in the community that people use to develop a lot of the theoretical results, which is essentially assuming TC0 is strictly smaller than NC1. And if that's indeed the case, then what this is telling us is there is a strict separation between the capabilities of transformers with COT or without COT. So these are really nice results because this sort of give us some confirmation that why having this kind of chain of thought reasoning is kind of necessary for having stronger capabilities of such models. But at the same time, it doesn't really answer the question why we see this kind of performance in practice. Particularly thinking about the transformers we are using in practice, actually the ones that we obtained by training them using simple gradient descent type of algorithms. So the question I'm particularly interested in today is answering questions like the following type. So imagine you have trained your transformers on some training tasks with some sort of length of reasoning length, right? So you train this within some constant, some sort of context length, and you were able to train the model to perform really well on the training data. So the performance is near perfect on those. But at inference time, you will be interested in deploying a model to problems that require longer thinking time. And the question is, can models that are trained to solve near perfectly these shorter tasks can really be generalized for solving these longer tasks? So potentially, you could either enter into the so-called generalization regime, right, where the model really learned how to solve the problem, the underlying skills, so it can really transfer the skills to solve longer problems. Or on the other end, maybe the model just memorized the training data, so it can solve really nicely the problem you see during training, but it cannot really generalize. So it is a priori, it is not clear what kind of mechanisms under the training, in trainings that really dictates this kind of length generalization capabilities. And this raises a question that I would like to be probing a little bit in the talk, is trying to think about these questions from the optimization perspective. Can we actually try to delineate these two types of behaviors by looking at the training dynamics of the transformers? So before our work, most of the problems that people have examined in practice in the literature are problems that really problem like, for example, parity problems. So those are actually problems within the TC0 where you actually do not really need COT to solve. While we are interested in, for example, thinking about problems beyond TC0, so that you actually indeed require this kind of sequential reasoning to solve. And hopefully, we'll be able to get a little bit more insights towards those directions as well. Before I enter sort of the more mathematical derivations, I just want to also show why this is an interesting problem. People have been also looking at this kind of length generalization issues from the empirical perspective. You don't have to read sort of what I put here, but this is just sort of samples of illustrations from various papers. But the message here is that we don't have a clear answer for these questions. That sometimes you read a paper that shows very nice length generalization. Sometimes people, these models just fail completely on some of these tasks. So it's not very clear what is the right verdict on these problems. So in this talk, we'll be trying to answer this from the training dynamic perspective. Yeah.
So is problem length really the right way to think about difficulty of the problem?
So there are different ways for you to think about how this generalization from easier problem to harder problems. So in my talk, as will be hopefully clear, is that at least for the problem we are studying, the way we think about difficulty is in terms of length generalization. So from shorter problem to longer problems. But yeah, definitely, I think there are a lot of different dimensions you can look at this. So that's sort of the limitation we have.
Yeah, so one quick question. So when people think about generalization, we think about generalization in distribution and out of distribution, right? So this generalization, occurred to me that it's kind of OOD type of generalization task. In the training data, you're not seeing any example like that. It's out of support. On the other hand, when people talk about memorization, I think from your previous slide, when you refer to memorization, it could very much be, perfectly generalizing for new data from the same distribution, and you are still calling that memorization.
Yeah.
Okay, yeah. So it's about OOD generalization, on the dimension of length.
Yes, so hopefully, so the intro is set a little bit more abstract, high level, but hopefully it becomes clear what I mean specifically in the problem we look at. Yeah, yeah. Other questions? That's great. Okay.
Just maybe I missed because what is Yuejie training?
I'll tell you more about it when I set up the problem. But a short answer is, so this talk only look at the supervised case. So where you actually give the underlying problem you are interested in solving requires some sort of step-by-step reasoning. And you'll be, in your training data, you'll provide explicitly what is step-by-step, every step in your training data. And the model is trained on the whole reasoning chain. But you could be just training on shorter problems. So problem requires smaller number of steps. But at generalization, you are interested in applying your model for a problem requiring a lot more steps.
I guess I'm trying to understand. I mean, in practice, I train on everything.
Yeah.
And so you cannot really say what I trained on in the training sense. I mean, are you thinking about kind of more toy models here or the?
I would say multiple models.
Multiple.
Yeah. Yeah, so the idea is that we'll be looking at the optimization side. So we'll be having some toy models. We'll be looking at how studying the training dynamic gradient descent, look at what sort of the characters you have at when the model converges for the trained attention patterns, and using those to answer generalization questions. Whether this kind of trained transformers can generalize to problems that hasn't been seen during training, and also maybe for longer lengths. So that's sort of what we'll be doing. And we'll be only looking at one layer transformers so that the analysis is tractable. But hopefully, at the end of the talk, I'll be able to convince you what kind of characters are important for you to at least make some prediction about the generalization capabilities. So that's the plan. And we'll be actually looking at two toy problems. They have a little bit different characters. So the first one is a path finding problem in trees. The goal there is to explore symbolic reasoning and understanding the role of multi-head attention. The second problem is a problem for doing kind of compositional reasoning. And in that model, we'll be actually also looking at the interplay of the attention module and the MLP module, and look at how the algebraic structure of your compositions actually is useful and actually critical for dictating your generalization capabilities. All right, so the first one is based on a joint paper with Tong, Yu, and Yingbin at New Reefs last year. So let me quickly introduce what the problem looks like. We actually look at two cases in this problem, and they are sort of built up with different levels of difficulties and complexities. So the problem is actually quite simple. Assuming you have this kind of, say, binary tree, and in your prompt, you'll be telling the model essentially all the edges in the tree, and you'll be telling the model what is the root node of your tree, and you have some sort of target or goal node. And the goal is to find the path between the root node and the goal node. So as you can imagine, it is easy to find the path from the goal node, the leaf node, so to the root node, right? Because if you do backtrack, there is only one parent node for each of the node in your tree, so that is relatively straightforward to go back. But the other problem, which is to do finding the path from the, say, the root node to the goal node will be harder, right? Because for your parent node, it can have multiple children nodes, so that you may not a priori know which one is the one you are looking for. So the way we've been set up the problem is actually to solve this forward reasoning, to solve the problem of finding the path from the root node to the goal node, you'll be actually first solve the problem of the backward problem. So you first find the path from the goal node to the root node, and then traverse that. So in other words, to solve this forward reasoning problem, you have to take double the length of the reasoning steps compared with the backward one. And arguably, you may also need to have a slightly more complicated transformer model in order to solve the second task. But having the first one is sort of nice to sort of warm up what we need, understand what we need, and getting a little bit of intuition about what the attention model does here. Make sense? Okay, so let's get into the model we are going to use. So the most important module here is this attention block, right? So I'm sure everyone probably knows about what this is, but just to set up the stage, the way we think about what the attention does is basically doing this kind of query in some sort of database, right? So you have, say, a bunch of this kind of key value pairs stored, and for any given query, you're going to match it against all the keys without data points, and then apply a softmax to make this into a score vector, right? That's sort of sum up to 1. And then you're just going to take a linear combination of the values with the scores obtained to obtain a retrieval item, right? So this is sort of what attention does. And importantly, if, say, your scores are highly concentrated on certain keys, then what happens is basically you'll be just retrieving the value vector associated with that particular key, right? So if you have this kind of what I call attention concentration, then the attention is essentially performing some kind of retrieval, right? Context retrieval to you. So that will be retrieving the important items in your context window. And this is sort of very important function that we'll be using a lot in solving our problems. Okay. So with this in place, essentially, when we think about solving, say, the simpler task of doing this backward task finding problem, it's more or less enough just to think about using a single attention head to do this. So this is just this looks a little bit different from what people typically see in practice, so that we actually simplified a lot of things. But at the end of the day, we'll be only training basically this sort of kernel-ish matrix within your softmax. So the goal is to train the attention module so that it can learn the associations between the embeddings. We are also assuming the embeddings are given, and we are only training the attention. So the way I'm going to set up the problem, or sort of describe what we have here, is we're going to first tell you the desirable attention patterns we want to solve the problem. In this kind of ideal scenario, when you expect you have some kind of attention concentration. And after I describe these constructions, I'll move to how you can design training distributions to actually, so that running simple gradient descent can actually find such attention patterns. So let me first describe how this attention look like. So at the beginning, in your input, you're going to put all the edges. So here, I just represent every edge by the index of the nodes, but you should think of them really as high-dimensional vectors, right? So every node has a nodal embedding that are given. And you also have the root node in your input, and you have the goal node. So you know that you are looking for the node 8 and want to find its path back to the root. Okay. So intuitively, the way you want to solve the problem is you'll be always, basically, when you calculate this sort of, you want to look into the historical context and find the one that's mostly correlated with it. So intuitively, in this case, we would like to have the attention scores to concentrate along, say, the one that's actually using this node, right? And this will be the edge 1, 8. And if your attention score can get very concentrated on this one, and then you can just say copy that as your retrieval. And by doing this repeatedly, you can just, in the next time, you'll be basically looking for the edge that's using, say, the node 1 and retrieve that one. Right? So this gives you a very natural step-by-step reasoning pattern that you just traverse the tree back to the root node. And by doing this, you'll be able to essentially solve this simple backward reasoning task using a single attention head, right? So you can actually ensure this construction always exists as long as you have some kind of linearly independent nodal embeddings. Questions? Good. Okay.
Can I click the OK
Hmm?
on the type on the slides, on top of slides?
Okay. Okay. So this mechanism, as I have described, really requires attention to be concentrated on around the desirable node, right? But you can kind of think, oh, sorry. Yeah. Okay. But you can imagine that as we move to the forward reasoning task, things become dramatically more complicated. There could be different constructions of the transformers for solving this task. But the one we have opted in is actually doing this kind of two-stage reasoning, where you actually ask the model to first do this backtracking. So it finds the path to the root node, and then it will essentially reverse the path. So that in the second stage, rather than reading directly from the edge set of the original tree, it will read in its COT scratchpad and reverse that path correspondingly. And this requires the model to automatically switch between these two different tasks. The first one is the backtracking one that's very similar to the one we've seen earlier. But the second stage is to basically do this COT retrieval. And in order to do this, we have to actually also introduce a second attention head into the model that we call this essentially a stage token, a stage signal that controls sort of the switch between the two tasks. And without giving all the details, the high-level takeaway is that the attention functions between the two heads are interrelated. So you have to use the output of the first head to figure out what you should be doing in the second head, and so on and so forth. So at the end of the day, this actually give us 6 different attention matrices that we need to track. But interestingly, at the end, it turned out that these 2 attention heads will do some kind of task. So they will have this sort of, each of them are taking responsibility for certain tasks. So the first head is essentially doing this edge retrieval that we are kind of seeing in the backward case. But the second head will be controlling the automatic task switch as it's controlling this task signals. So let me just show a little bit of the mechanism of sort of what is desirable at the end of the day. But on a high level, for the first in the first stage, this is very similar to what you see earlier, that the first attention head will be doing this kind of copy pasting, but it will still require it to pick at the task stage signal so that it knows it shouldn't be copying itself, but rather it should be copying in the original edge set. Then at the turning point, this is a sort of important in the sense, this is a point that the transformer should automatically realize it has reached the root node. And this is a point where the stage signal need to switch so that it knows that it has to change the direction of the output. And all this has to be done very carefully in sort of the design of the attention matrices. And once we are past this turning point, we're back into this kind of backward reasoning, kind of doing this copy and pasting stage. But in this stage, we have to be careful that what we are going to be outputting should be copied with from the output of the first stage, rather than from the original edge set. And this is again controlled by looking at the stage signals. So with all this in place, and you can indeed show, you can construct these attention matrices, and the construction is actually not unique. So you can actually construct a family of attention patterns so that at the end of the day, it can actually implement these mechanisms. And the main takeaway here is that in order to solve this kind of more complicated multi-stage reasoning problems, it seems necessary, at least more tractable when you have multiple attention heads being put into your model to take care of different pieces of the information flow. So, and the model should be doing this in an autonomous fashion. So there is nowhere in the middle of the reasoning steps that we are intervening the model to tell it to do this switch, but the model actually does so automatically. Okay, so these are sort of giving you the information about the construction of the attention patterns to solve these problems. But still, the main important question is how the trained transformers can actually learn such attention patterns. So the way we set up the training task is that we basically train these models on a family of distributions. So at the training time, we basically give the model random perfect binary trees to look at. And we just randomly specify, say, root node and goal node. And we give the model the perfect reasoning, reasoning chain. So all the intermediate steps that you're seeing in the previous steps for the model to look at. And also for the analysis, we are assuming all the embeddings are also normal. So this is for simplification. You can change this to linear independent embeddings, but just the analysis becomes more complicated. And once you have all this training data in place, yeah.
Are you using positional embeddings?
No, that's very important, yes. So thank you for the clarification. So there's no positional embedding. So the point being, you can actually swap these edges in your context with no positional bias, right? Yeah.
Do you think you can go down to one attention head if you added positional embeddings? So I imagine you can do some clever position information to reversal.
So in this task, I think one of the reasons we don't do this is also because at generalization, at inference time, you can apply this to longer trees. So having the positional embedding may break the generalization. Here, the point is that as long as you learn these attention patterns, so you know what are the information you want to achieve in terms of the edge associations, intuitively you will be able to generalize. Right? All right. So the training algorithm we'll be gradient descent, and by doing chain of thought reasoning training, what I mean is we do this kind of teacher forcing so that at every time we give the model what you know after say k step, and we ask the model to predict what would be the right output at k+1 at every step. We are not really doing something, for example, you let the model infer every step and match that. But at inference time, we are now giving the model intermediate supervisions. But only at training time, we are doing this kind of intermediate supervisions. And the training loss is just a very simple least square loss in this case. And the algorithm is also standard gradient descent, where all the initial parameters are initialized at 0, which means at the beginning of your training, all your attention patterns are uniform attention. So you are not giving any specific preference to things in the context window.
So you're saying the input up to k-1 is generated by the expert.
Yeah, so you have the exact, the correct steps, but you are only predicting the next one.
Yeah, I see. That's interesting.
So this is, I should say, this is very common for this kind of COT reasoning settings for the supervised setting, because you assume you have the entire reasoning chain, and so this is doable.
So
Which is
offline setting.
Yeah, which will be very different from, for example, you want to do an IO setting where you don't have intermediate.
Yeah, so that having in mind the kind of regular, right? So you get start players will run and then you.
Yeah, so this would, yeah, exactly. Yeah.
This is a harder problem, right? Because you have to kind of handle distribution shift induced by the induced state distribution.
Yeah, so what you describe will be hard. This is easier because we don't handle the distribution shift, right? So we assume you have all the perfect information, all the perfect predictions up to step K. So those are given by your training data, your reasoning traces. You only predict the next one. Yeah, but at inference time, you don't do that. Yeah.
So at inference time, suppose your training model run into a state you have never seen before, then it still works, or you kind of can bound the problem.
So that, yeah, yes. So that's precisely what we do. All right, cool. So under this kind of settings of the training distribution, and also the training algorithms, we can actually guarantee convergence. So this slide shows the training time convergence. So you can drive the training accuracy arbitrarily small up to some accuracy level epsilon with this number of iteration complexities. I will now read these expressions off, but intuitively doing the backward reasoning converges at faster rates, right? Because you're only training one attention head, while in the second case, we're training significantly more parameters, so it takes longer to train. But with this in place, we can also talk about generalization. So at generalization time, we are now doing this teacher forcing. So you let the model just infer every step. And you can also allow the model to be applied to an arbitrary tree, of course, up to some cap of sort of dimension embeddings. So you can actually apply the model to a tree with more nodes, longer, right? Deeper paths. The path length can be longer than what is have seen during training. So those are parameters given by n tilde and m tilde, and n and m are what you've seen constructed at training time. So the point here is essentially a test performance is some prefactor times the performance you see at training. So in order to get generalization, essentially, as long as you drive your training performance sufficiently small, you will be able to drive the test performance also to be reasonably good. And the reason this happens is because, as I have tried to describe in the mechanisms, what is really required for the model to generalize is how this attention patterns concentrates to the desired patterns. And we can drive this attention pattern to be concentrated almost arbitrarily well, at least in these toy models, by driving the training performance to be accuracy to be epsilon to be small. So as long as you can train sufficiently longer, you can generalize to longer lengths during inference time. And having no position, no embedding, I think helps in these cases because precisely we are learning this association. So rather than what I call these skills, right? Rather than just memorizing where at which positions this node has occurred. All right. So this is just a toy illustration of sort of the training dynamic for the forward case. One thing I want to highlight is that in this two attention heads, there's as you can see, they are now the first has related to the edge retrievals are kind of behaving in a kind of more expected manners that you just try to concentrate on the right edges. But the second attention head actually goes through some quite interesting non-monotonic behaviors that we have to control very carefully. But at the end of the day, as long as the first head is somewhat trained to a reasonable accuracy, we will be able to control also the behavior the second has, and they almost converge at the same rate. So that's sort of the final takeaway. Yeah.
Yes, sir. And so during the training, how many trees do you have?
So okay, great. So these are we only analyze population loss, and we also only the reason and then we only analyze this kind of binary perfect trees because it has a lot of symmetries, right? So we can simplify a lot of the dynamics to make it more tractable. Otherwise, there's just too many things. It will be very interesting to think about generalizing this to like a sample complexity analysis.
In the training data, are you only using trees of the same depth or depths that are uniform between 0 to 2?
Yeah, so it's a fixed depth.
Okay.
And a fixed number of nodes. Yeah.
So, since here you are using like autonomous embeddings, so basically the security lens is founded by.
Yeah, exactly. So this generalization lens, like these things will be confined by your embedding dimension.
I think so.
Yeah.
For example, here, then what could be the factor that can tilt over or not? And then
So I think that, yeah, so the limiting factor will be S. So S is, so this is, N is kind of the total number of nodes in your tree, right? But S is some larger number. So this is kind of embedding dimension. So for example, you can have S to be 1,000, M to be 3, right? Something like that.
And the problem doesn't depend on the dimension.
It depends on, so we put S there.
Oh,
So using S, the larger number there, yeah.
okay, I noticed the learning rate over there. Are there constraints on learning rate? Otherwise, like learning rate can be arbitrarily large and T, is complex.
Yeah, because, yeah, it's in the paper. I don't remember the exact expression. I think there's some constraints. All right, cool. So let me now move to the second one. This is about compositional reasoning. And one thing we want to, so one of the motivating problem we have here is about state checking. And this has been becoming quite interesting and I think useful for, particularly in some of the maybe more recent agent settings, people are using this quite heavily. So the setting for our study, we actually use this so-called Lego task proposed by Microsoft a few years ago. The way this problem is formulated is essentially, let's say you have a sequence of equations. You have a few variables, say this x1, x2 variables, and you have some maybe group actions. So this is G's, some sort of group actions are taken from some group. And you, in your predicate clauses, this is where how you define your problem. You have basically this kind of group actions applied from the beginning, the initial variable x0, and then you apply g1 to get x1, and then apply g2 to get x2, and so on and so forth. And in your answers, you're assuming you have the first, you know the value of the first one, so you know the initial value of x0. And based on this sequence of equations you have in your predicate clauses, you will be able to infer the value of the rest of the variables by doing a chain of thought reasoning. So intuitively, the chain just looks like applying this sequence of group actions to your variables. And with the starting point, you can imply each of the variable on your chain. So a typical example will be doing some kind of modular sum or parity check, where you have a sequence of equations, right? And you have the initial point, you can infer what the rest of those are. In this problem, we actually assume you have to also learn the G's, okay? And intuitively, the model you can learn the G will be applying some kind of MLP, right? So let's just talk about the architecture we'll be using for solving this problem. So let's assume you have this sequence of equations and you're up to solving the variable xm, and interested in solving the next variable. The first thing you need to know is to do some kind of attention mechanism so that you know at the next step, I'll be using this clause to calculate the value of xm plus 1. And I know that the group action I should be applying is gm, right? And I know my current value is ym. So if you have these three things, you will be able to basically learn what the next value is by doing some kind of MLP operation. So you can just think of this as a high-dimensional function mapping that maps different combinations of x and y and g's, right, to the correct output. And your attention is doing this sort of association. So it needs two important attention patterns. One is the self-attention, right? Attend to itself. And the second one is attention to the correct predicates in your context. Yeah.
How's the group encoded into?
Yeah, so again, you'll be having some like a high dimensional embedding vectors. So in the paper, I think,
So to find it.
yeah, so I think in the paper, we're doing some one-hot embedding. Yeah. Yeah, so you could intuitively think you have all these vectors as high dimensional embeddings. For every combination, you know what the output should be. Yeah. And that can be done by learning MLP. And in fact, to learn the MLP, you only need essentially one step, right? That's all you need for getting that association. All right, so let me, I will not be able to give you all the details of the setup for the sake of time. But some of the high level things I want to emphasize is that, so the way we set up the problem is that we'll be embedding every sentences, these clauses. And then from COT prediction, we'll be doing this kind of next answer prediction. So at every time, we'll try to predict the entire answer sentence rather than each of the underlying X and Y's individually. And we'll be using a cross entropy loss for doing this. In terms of training dynamics, again, the important thing is to track how this attention patterns concentrates on the important clauses and the queries. And that is important to think about the length generalization capabilities. So here, by length generalization, what I mean is in training, you train on shorter legal questions, but at inference time, you're interested in answering questions require more steps. All right, so this is sort of what the attention part look like. There, as I mentioned, there are two important attention quantities. One is trying to attend to the correct predicate. But the second one is self-attention. At the time of convergence, you would want this attention, this two attention, to be concentrated near one. At the initialization, you will have a uniform initialization. So essentially, the training dynamic cares about how the attention concentrates towards one to solve this problem. And in order to talk about sort of the results, it turns out the structure of the group actually plays an important role. We sort of single out two cases. The first one is what we call a simply transitive case. This is where you think of, when you think about the group actions, it's actually relatively straightforward. If you take any pair of Y's, there is a unique group element that maps a Y to a different Y prime. And this kind of uniqueness really helps you to learn a good concentration pattern for the attentions. On the other end, there is also a case that we call the symmetry actions. This is where you have potentially many different group elements that can map a Y to a Y prime. For example, you can imagine this is a case where you apply a permutation group to integers of n elements. And this will include problems strictly go beyond TC0. And as we'll see, they will have very different behavior in terms of generalizations. So for the first case of the simply transitive case, we train the model on length 2. So what happens is at length 1, essentially, you can learn the MLP very well. There is really no need to learn the associations because you are simply trying to predict X1 from X0. So you can learn MLP very well just by using length 1. And then at length 2, you can learn the attention patterns. And it turns out that you can already learn the attention pattern really well there, so that at the generalization time, you can already solve problem of much longer length, up to some d to the, say, 0.2, some small constant order. So d is roughly, say, the longest generalization you can imagine in terms of the embedding dimension. So intuitively, what happens is, what we can show is at the end of training, in this simple case, the attention concentrates really well. So you can drive this to be a level where this attention pattern is concentrated around 1 up to 1 over DC order. And this number really controls how much sort of dilution you can handle at generalization time, when you see a lot more distractions, different clauses in your context. Because of the attention concentrates show so well, you can actually handle dilution up to an order d to the c. So you already have very good generalization, even by just training on length 2. Okay. However, in the second case, if you have a group where there are a lot of ambiguities, so even by using, you can have different G's, different group elements that map your Y to Y prime, you will have a lot of trouble because in this case, at the time of convergence for your training data, you can really not sharpen the attention well enough. So at the end of the day, the attention only concentrates around 1 up to some small constant. Intuitively speaking, this is when you can essentially have the perfect performance on your training data. But you are not really learning the right attention pattern you want due to all this kind of ambiguities, or what we call distractors in our paper. And if this is the case, you will not be able to obtain direct length generalization, as you see earlier. In fact, you can only guarantee some kind of constant factor generalization, which is a little bit depressing. But turns out this kind of constant factor generalization can actually already enable some kind of self-improvement loop. So what we mean by this is essentially we start the training at length 2, even though we cannot show direct length generalization long enough, but this is good enough to get the length generalization with a factor of 2. So we can already generalize to a length 4. And we can use that model actually to self-label a new data set of length 4. And on that data set, we can further train the model to generalize, say, to length 8, and so on and so forth. So if we do this, then essentially with log D number of rounds, we'll be able to get the perfect length generalization that up to length D, right? And this is sort of allows us to solve problems that goes beyond the TC0 with optimization guarantees. All right, so this is just a numerical illustration that indeed this is also consistent with what we'll observe in practice. So this is basically just experiments done exactly on the model we analyzed in the paper, that you see that basically for cyclic group, this kind of simply transitive groups, even by just training on length 5, you get very nice length generalization across the board. But with the symmetry group, the length generalization performance drops significantly, even with a little bit of longer length. But as you can already see, even though we don't get very far away for the length generalization, we do get a little, so that we can enable this kind of self-improvement loop where we use a model that is we obtain from length 5 training to train another model at length 10, so that we get this green curve, and then we can do this again to get this length 20 and so on. So even with a small number of rounds of self-improvement, we can dramatically improve the performance of the model in terms of its length generalization capabilities. All right, and this just shows that because we don't do any positional embedding, so you can actually arbitrarily, you can permute the order of the predicates, and the model will be pick up the right attention pattern through training. So the result will be now be sensitive to the position of the clause. You don't have to have them in the same order as we described in the slides. All right, I think this comes to the end of the talk. So hopefully I was able to tell a little bit of story along understanding the training dynamics of one-layer transformers, which arguably is a very simple model, But I think the takeaway here is that by doing this kind of chain of thought reasoning training, we were able to delineate the story that essentially this attention concentration mechanism is what we think is important with reason about the capabilities of models, less generalization capabilities. So in both cases, what is important for the model is essentially some kind of repetitive or recurring application of the same kind of attention or retrieval skills over time, over length. And this is when the attention concentration really matters. One of the interesting direction we are currently working on is actually thinking about how to get rid of the intermediate steps to do some kind of IO training. We actually just released the papers 2 weeks ago on arXiv for understanding the training dynamic of IO for such length generalization problems. So if I'm interested, I'll be happy to talk about that in our one-on-one meetings or off the talk. I think that's all I want to share today. These are the papers, and if I'm interested, I'll be happy to answer questions. Yeah, thank you so much for your attention.